let's continue. Let me open the table of content first. Okay, we are on chapter 26. Okay, now let's check that out. If I remember correctly, we are on this section, an example thread creation. Let me open that. This one. Okay, let's check this example. T0.c. Okay, you can take a look at this in the description, I guess, or let me copy this in the chat in case anyone wants to take a look. Where is it? Threads intro. Okay, this one, I think T0.c, right? T0.c. Okay, but yeah, where do we got this common underscore thread? Let me check the makefile. Oh, okay, include. Oh, let me check that. Include here common and common thread. Get time. Do we use get time? I don't think we use get time here. Well, let me open my terminal emulator. Chapter 26, I guess. Okay, not that one. T0.c. I mean, we didn't use the argument, right? Okay. Okay. Times that assert. Oh, maybe with the assert here. Okay. Let me check. Oh, we also include assert in here. Okay. Oh, adding semaphore. Interesting. Let me check. Semaphore. Okay. Define same type. I don't think we need to include semaphore header for this example. So we might need bitrate here, right? No, not that one. Bitrate. Okay. Bitrate underscore T. It's nothing perfect. Oh. put something like this. Let me check. Maybe this is in the bitrate header. Maybe. Okay, include bitrate. Okay, and then we add this. I guess STDIO. P1 and P2. Let's exclude that first. Chapter 26. Not that one. T0, I guess. Okay. Chapter T6, T0. Okay. And then let's create this first, I guess. Void my thread arc. Yeah, I prefer to have a function prototype and then define that later on. This is just personal preference, I guess. Okay, we need to that kind of interesting. Do we need to have this void pointer bitrate create? Let me check. That create. Okay, that argument start routine bitrate create. Okay. Start routine. Okay, there is the main page, the manual page. Okay. Oh, right. Void pointer. Okay. Wait 2 minutes. Start routine, right? Okay, function pointer. Function pointer with. Okay. I mean, I'm kind of curious. Can we like use from this one, right? It looks like start routine is a function pointer to the function with return value void pointer and parameter type void pointer too. and nullable. And we can ignore this maybe. But yeah, let's try this first, I guess. Because we are using the void pointer here, we need to, what is it called? We need to guess to the specific pointer here. In this case, char pointer, something like this, return null, okay. And then integer RC. Where do we use the RC here? Yeah, where do we use the RC? We use P1 here. This one is null, okay. Okay, my thread A and P. Wait for the threads to finish. Interesting. Do we need RC here? Wait a minute. Let me check. Where is it? Thread intro, okay. T0. Now we are checking the argument count. Oh, in case we provide some kind of argument, I guess. Okay, right. There is no RC here. So I don't think we need RC here too. I mean, we didn't use RC anywhere, as far as I know, right? Okay, so yeah, and then going to this, put main begin, and then feed thread create. This one, the macro, okay. It's basically just, what is it called? Bundle this with assert, I guess. Checking if the result is 0. Return value. On success, we thread get return 0. On error, it returns an error number, and the contents of a pointer thread are undefined. Okay, so maybe we can do something like this. P1. Oh, okay. Maybe we can use this RC as the return code or return value, maybe. So maybe we can do something like this. Return value, pthread, create, and then of course this one, right? null. Okay, we are not using this attribute, I assume. I'm still not sure what kind of attribute that is. So let's use null and then start the routine, right? Use my thread here. And the last one is the argument. Argument for the routine, I guess. Maybe something like this. If red file not equal 0. Well, I forgot what it is. Yeah, let's return 69 and then return value. Okay, did it? Oh, okay, maybe it, what is it called? Maybe it said error no, right? So maybe we can do something like this. Or rather than doing something like this, you know what, let me check. Maybe in this one, or maybe line. Yeah, like saving the string error from the errno. Something like that. Is the errno? Okay, it looks like it is in the string header. Okay, let me add that, I guess. And air constant. Okay, constant air. Okay, errno. I think I also need to include errno. Let me try. Right, include errno. At least at compile, whether that is correct or not remains to be seen. Thread create fail line. Okay, and then error, the line number here. Okay, unsuccess, only return 0 unsuccess, right? Other than that, we assume it is an error. Okay, there is that, I guess. Wait. B, okay. And this one is B2, right? It is identical except for the argument for my thread, this one, which will be what is it called? Casting to char pointer. That make me curious too now. Maybe we should cast this to const char. Maybe we are not gonna change that anyway, right? Okay, join waits for the thread to finish. Okay, join, Peter join here. Okay, basically if it is not 0, the return value of Peter join, we will throw an error. Okay. Pthread join, masuk an integer return value the thread, and then redfall. If redfall is not null, then pthread join copies the exit status of the target thread. That is the value that the target thread supplied to the target value that the value that the target thread supplied to pthread exit. Into the location pointed to by redfall. If the target thread was cancelled, then pthread cancel is placed in the location pointed to by redfall. Okay, I guess that's why it is a pointer to pointer. Maybe. Okay, let's use null for now. Redfall. Okay. Pthread join, right? And then the thread, let's say P1. The next argument null. Okay. Alright, I need to know the return value, okay? Unsuccess return 0. On error it returns an error number. Alright. For not equal 0, we are doing this again. Join. Okay. V2. Alright. And then, okay, the last one, print main n. have main begin, right? And there's also main end here. Okay. Let me try compiling that. Alright. Main begin, A, B, and then main end. Is it always the case? I'm still not sure. After creating the two threads, let's call them T1 and T2. The main threads call vthread join, which wait for a particular thread to complete. It does so twice, thus ensuring T1 and T2 will run and complete before finally allowing the main thread to run again. It does so twice, thus ensuring T1 and T2 will run and complete before finally allowing the main thread to run again. When it does, okay, wait a minute. Oh, let's wait for a particular thread to complete. The main thread calls vthread join, which wait for a particular thread to complete. Waits for the thread specified by thread to terminate. Okay, if the thread has already terminated, then vthread join returns immediately. The thread specified by thread must be joinable. Okay, so the wait process in this one vthread join, right? So if we comment this out, I assume we didn't wait for the thread to finish or terminate. Maybe something like that. Oh, is the thread gonna be finished or not? Or become a zombie process? Interesting. Oh. If we add for the thread A, the thread B also appear. Interesting. If we wait the last thread, thread A and B appear. Yeah, I'm still not sure how this works yet. Terminate, something like that. Okay. It does so twice, thus ensuring T1 and T2 will run and complete before finally allowing the main thread to run again. When it does, it will print main end and exit, right? After this thread P1 and P2 terminate, we print main end here and then return or exit. Okay. Overall 3 threads were employed during this run. The main thread T1 and T2. Let us examine the possible execution order of this little program. I'm kind of curious. Let me... I guess... So this may be constar. What is it called? A1 arc, maybe something like that. A and then this one B. Okay, and then we can change this. Something like this. Okay. Alright. Try compare that. Oh, okay. Discard cons. Alright, yeah. Okay. Can do that. Alright. Yeah, if we put cons to the non-cons char, that might cause some problem, so something to keep in mind. Okay, let us examine the possible execution order of this little program. In the execution program, figure 26.3, page 5, time increase in the downward direction, and its column show when a different thread, the main one or thread 1 or thread 2, is running. The possible execution order of this little program. In the execution diagram, I think this one, figure 26.3, thread trace 1. Okay. Time increase in the downward direction, and its column show when a different thread, the main one or thread 1 or thread 2, is running. Alright. Time increase in the downward direction. Okay. Start running, print main, begin, okay. Create state 1, create state 2, wait for T1, and then inside of thread 1, runs print A and then returns. Okay. And then after the thread 1 returns or terminate, wait for T2, and then inside the thread 2 or T2, we print B and then return. After that we print main end. Okay. Time increase in the downward direction. I don't really see any time information here. So, okay, I'm not sure what about that time here. Okay, note, however, that this ordering is not the only possible ordering, right? In fact, given a sequence of instructions, there are quite a few, depending on which thread the scheduler decides to run at a given point. For example, once a thread is created, it may run immediately, which would lead to the execution zone in figure 26.4, page 5. This one. Thread trace 2. Okay. We could even see B print before A if, say, the scheduler decided to run thread 2 first. Even though thread 1 was created earlier, there's no reason to assume that a thread that is created first will run first, right? There is no guarantee that a thread created first will run first. Figure 26.5, page 6 shows this final execution ordering with thread through getting to start stuff before thread 1. Maybe we can emulate that something like this. Basically, we wait for the P2 first before running the P1. Maybe. Oh no, okay. Interesting. So not like this one. As you might be able to see, let's continue first. One way to think about thread creation is that it is a bit like making function call. Wait, you know what? Let me check this figure 26.4 first. Start running, prints main, create thread 1, runs, print, okay, return, create threads 2, then print P, return, wait for T1, return immediately because thread 1 already done. This one also the same, return immediately because T2 is done, and then print main n. Go 26.5, thread trace 3, print, create, okay. Yeah, how do we do this? Run, print P, return, wait for T1, okay. Doing this, and then when we wait for T2, we return immediately because thread 2 already done here. Maybe. Okay. As you might be able to see, one way to think about thread creation is that it is a bit like making a function call. However, instead of first executing the function and then returning to the caller, the system instead creates a new thread of execution for the routine that is being called, and it runs independently of the caller. Okay. A new thread. independently of the color. Okay. Perhaps before returning from the create, but okay, perhaps before returning from the create, but perhaps much matter. What runs next is determined by the operating system scheduler, and although the scheduler likely implements some sensible algorithm, it is hard to know what will run at any given moment in time. The scheduler likely implements some sensible algorithm. It is hard to know what will run at any given moment in time. As you also might be able to tell from this example, threads make life complicated. It is already hard to tell what will run when. Computers are hard enough to understand without concurrency. Unfortunately, with concurrency, it simply gets worse. Much worse. Okay. Yeah, I'm kind of curious how we can do this. Running the thread 2 first before thread 1. Hello, Undermines. Oh, you're already playing C Pro? Yes. I've tried C programming language before. Oh, this is like a parallel, right? Well, I think, what is it called? There is some difference between concurrency and parallel, but the concept is kind of the same maybe. Like we are running, what is it called? Running something at the same time, maybe something like that. But the different, yeah, I'm still not sure, but I've read somewhere that concurrency and parallelism might be different. Yeah, this is one of the, what is it? The major reason of using concurrency, that is parallelism. Or maybe it is something different. Yeah, I don't really remember. But from this book, right, why use thread, or maybe concurrency in this case, I guess. Yeah, one of the reasons because of parallelism. So we are using thread to, what is it called? To emulate parallelism, maybe something like that. So imagine you are writing a program that performs operation on a very large array. Okay, adding two large array together or incrementing the value of each element in the array by some amount. If you are running on just a single processor, the task is straightforward. Just perform its operation and be done. However, you are executing the program on a system. However, if you are executing the program on a system with multiple processors, you have the potential of speeding up this process considerably by using the processor to each perform a portion of the work. The task of transforming your standard single-thread program into a program that does this sort of work on multiple CPU is called parallelization. And using a thread per CPU to do this work is a natural and typical way to make program run faster on modern hardware. Let me check. Computer difference between concurrency and parallelism. Okay, wait a minute. Let me solve this CAPTCHA and see if I am the robot or not. Okay, I am the robot. It looks like the actual intelligence, the actual Indonesian, I mean. Where is it this one? No. Oh, this one. Okay. Yeah, I read somewhere that concurrency and parallelism might be different. Concurrency is a two-line of customer ordering from a single cashier. Lines take turn ordering. Parallelism is two lines of customer ordering from two cashier. Okay, each line get its own cashier. Okay, and maybe something like that. Can a single core processor run parallelism? I don't think so. I mean, it depends on the thread in the core, I guess. If the core only have one thread, then no, I don't think we can do parallelism, because again it will become the single thread application, and parallelism need multi-thread processor, something like that. So what determines whether a program runs in parallel? Is it software or hardware? Program runs in parallel. Is it software or hardware? As far as I know, it might be from the software side. So the software tells the operating system that this software or this application need to run in parallel. Maybe something like that. And then the hardware, what is it called? Adjust that or something. So I assume what determines that is from the software side or from the application side, which means if we didn't tell or didn't specify the application to be a multi-thread application, we might be running in the single thread here. Our application or program or software will be run as a single thread program. Maybe. But yeah, I think it depends on the application, I mean the programming language, maybe. Some programming language might be run the, what is it called? Run the application as a multi-thread application by default. Maybe. I'm still not sure about that. But from what I understand, we need to specify whether it is multi-thread or single thread from the software side. And then the hardware will adjust to our need. Maybe something like that. Okay, because program like Cinebench are for testing single core or multi-core CPU core. I'm not sure how Cinebench work yet, so I cannot comment on that. But yeah, from my understanding, at first, the hardware will assume we want to use a single thread, or let's say one CPU, right? Rather than multiple CPU. And then some application tell the hardware, oh, we want to use multiple CPU if you have more than one CPU. And then it becomes the multi-thread application. Where is it? This one, multi-thread program or application, or whatever you named it. So yeah, the default is single thread, and then we need to specify in the software side or in the application side, do we want to run this as a single thread or multi-thread? As far as I know, which mean can be wrong. I'm trying to understand this too. Okay, let me copy this, I guess, in the chat in case anyone wants to take a look the difference between parallelism and concurrency. Yeah, multi-thread programming, right? Condition that exists when at least two threads are making progress. A more generalized form of parallelism that can include time slicing as a form of virtual parallelism. Okay. Parallelism, a condition that arises when at least two threads are executing simultaneously. Okay. Maybe the key point here is simultaneously at the same time. Maybe are making progress but not at the same time. Maybe something like that. Let me check this, I guess. From the Haskell wiki. Oh. Multiple processor to gain performance. Parallelism has no semantic impact at all. It's executed sequentially or in parallel. Concurrent program has concurrency as part of its specification. The program must run concurrent thread, each of which can independently perform input or output. The program may be run on many processors or on one. Oh, that is an implementation choice. Right, we can determine whether we want our program to run on one CPU or multiple CPU during the implementation of the program. The behavior of the program is necessarily and by design non-deterministic. Hence, unlike parallelism, concurrency has a substantial semantic impact. Yeah, let me copy this in the chat. If anyone wants to take a look. But yes, if I remember correctly, there is some difference between concurrency and parallelism, but I'm still not sure which one is correct. Again, I'm still trying to figure this out. Which is faster, concurrency or parallelism? From my understanding, Probably the parallelism, because I assume parallelism need to have at least two two thread, I guess. So maybe parallelism is like running, what is it called? Maybe something like this. Rather than having one cashier, we have two cashier to serve two line of customer. But concurrency, we might only have one cashier, but we need to serve two line of customer in the one cashier. So it's like, what is it called? Joining the line into a single cashier instead of two cashier like this. So each line get its own cashier. Maybe something like that. But then again, yeah, there's a lot of confusion. So I don't really understand which one is correct. This might be an interesting read. In case anyone wants to take a look. Okay. We are taking a look at that. May it get worse? Oh, there is also code here. Okay, I guess let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.